Hello friends, in this video today we are going to discuss about operators. So let's start the class. So what is operator? An operator is a rule is a rule sorry is a rule which changes a function into another function. Suppose we have a function f of x. Suppose let us have sin x. This is a function of x. So if you differentiate it, that is also an operator with respect to x, then you will get then you will get cos x. This is another function of x. So here this d by dx differential coefficient is the operator in this case. Okay, now we may have different type of operators: linear operator, identity operator, null operator, inverse operator, and so on. So let us discuss those things. So what is linear operator? Now you see, an operator, suppose we have p cap, is said to be linear if it satisfies the following conditions. What are the conditions? Suppose we have two arbitrary functions f and g. We have suppose two arbitrary functions. When it operates, this operator operates on f plus g, then it gives it's equal to p operates on f plus p cap operates on g. So f and g, these two are arbitrary functions. And it must also satisfy this condition as well. P operates on a constant, suppose c we have, and a function, suppose f, who is going to be equal to c. P operates on f. So if an operator satisfies these two conditions, then it is said to be linear operators. So now you see, let me give you an example of linear operator, not only one. Here you see identity operator and null operator. These two are linear operators, identity operators. Identity operator. So it is a linear operator. Now you see, what do you mean by identity operator? An operator, suppose I cap, is said to be identity operator. Identity operator if this I cap operates on a function. Suppose we have a function, let me take that function as psi, suppose, then it gives again psi, then it is said to be identity operator. So hope you have understood that. And null operator, or you can say zero operator, null operator. So suppose an operator O cap is said to be null operator if this operator operates on a function. Let me take any function, suppose u, and it gives 0, then it is said to be null operator. Now let me tell you one more important thing on operator. Suppose you have any operator a cap, and if it is a square, a cap square means this operator a cap operating on a function twice. Okay, operating on a function twice. Suppose when we take second order derivative with respect to x of a function, suppose we have taken the function is, suppose, let me take x cube. Okay, so what does it mean? That means we operate this function by this operator twice. If you differentiate it once, then you will get 3x square. Then if you differentiate it again, then we used to put power here, so then it will be 6x. So that is so inverse operator. What do you mean by inverse operator? Suppose we have two operators, one is a cap, another is b cap, and a function, suppose u. When a operates on u, it gives, suppose, v, another function v. Okay, and again, if b operates on the function v, if it gives u, then these two functions are said to be inverse of each other. Okay, inverse of each other. So that means then here you see b inverse function, when it will operates on u, it will give v, isn't it? That means b is the inverse function of a cap, b cap is inverse function of a cap. So hope you have understood what is inverse function. So let me write the definition here. Sorry. If a cap and b cap be two operators, or you can say are two operators, such that when a operates on u gives v, and when b operates on v gives u, then b cap is the inverse function of a cap. So that is the definition of inverse function. So similarly, a cap will be said will be called inverse function of b. So that's why b cap can be written as inverse of a. So hope you have understood what is the inverse function. Now, so what is eigenvalue and eigenfunction? Now suppose we have an operator p cap and it operates on a function psi, and it gives the same operator, okay, psi, and suppose we have got a multiple this is lambda. Okay, it may be real or complex. So in that case, this lambda is said to be eigenvalue of this function, and this function is this lambda is eigenvalue, and this function is eigenfunction, and this equation is called eigenvalue equation. So hope you have understood this. So that means now you see this operator operates on psi, again it gives psi, and this lambda is, it may be real number or it is maybe it is complex. Okay, then this is eigenvalue equation, and this function is said to be eigenfunction, and this value we have got here, this lambda, is eigenvalue. So hope you have understood that what is eigenvalue, what is eigenfunction, and eigenvalue equation. So now let us discuss about a few important operators in quantum mechanics. Now you see, for a free particle moving in x direction, so the wave function is given by psi x, psi of x and t is given by a e to the power I by h cut into px x minus e into t. This px represents momentum here. So hope you have understood this. Suppose this is equation number 1. Now if you differentiate this with respect to x, del psi by del x, then you will get a I by h cut px e to the power I by h cut into px into x minus e t. Now here you see, if you compare this term, a into this is again equal to psi. So that's why from 1 we can write this equation as del psi by del x I by h cut px psi from 1. Okay, we can write this way. Now you see, this implies h cut by I del by del x of psi, this operates on psi, gives px psi. So here you can see, when it operates on psi, it gives px psi. So that's why we can consider this one as an operator. So it is associated with this momentum, that's why it is momentum operator. So we can write that px, we used to write cap on that px to represent the operator, which is h cut by I del by del x. So this is nothing but, this is the momentum operator. Momentum operator in 1 dimension. And in 3D, instead of del by del x, we will write del operator then we will write only p cap, that's going to be equal to h cut by I, this del operator, and this is in 3D, this is momentum operator in 3D. So here what we have done, differentiating with respect to x, that's what we have to write here. So hope you have understood now. So what is the kinetic energy operator? Let me explain that. Now let us give it this is equation number 2. If you differentiate this equation again with respect to x, then what you will get, differentiating equation number 2, with respect to x again, then what you will get, then this equation number 2 implies h cut by I, second order derivative with respect to x, operates on psi, then gives px del psi by del x. That's what you will get. Okay, now that here you see, this del psi by del x, it can be replaced by this, here you see. So let me use another ink. So instead of del psi by del x, we can put this I h cut px psi. So let us use that here. So now here you see, if you use that, then what you will get, I by h cut px square px square psi, that's what you will get. Okay, now if you simplify this equation, so here you see, this is I. Okay, so if you simplify this equation, that's going to be minus h cut square second order derivative with respect to x, operates on psi, and here p px square psi. That's what you will get. Suppose, let us consider this is equation number 3. Okay, so that's what we have got. Now if you divide this equation by twice m, dividing, sorry, so simply write this way, dividing equation number 3 with twice m. Okay, then what you will get? Then you will get minus h cut square by twice m, second order derivative with respect to x, which operates on psi, gives px square by twice m psi. That's what you will get. And let us represent this term by k. Okay, so then what you can write this equation can be written in this form: h cut by twice m, okay, second order derivative with respect to x on psi, this k psi. This is suppose equation number 4, and where k is nothing but px square by twice m, which is, and px square twice m, this is nothing but, this is kinetic energy. Okay, this is kinetic energy. So in the Hamiltonian equation that we have got, this h is equal to px square by twice m plus v. That's what we have got, isn't it? That this part is T, that is kinetic energy, this is potential energy V. So we know that, isn't it? So here, that's why we can say that this is the kinetic energy operator. So k cap is equal to minus h cut square by twice m, second order derivative with respect to x, and this is kinetic energy operator in one dimension. So in 3D we will get k cap, that is equal to minus h cut square by twice m. This is Laplace operator. So this is in 3D. So that is our kinetic energy operator. Now what will be the total energy operator? So now you see total energy operator. Now you see a particle moving in a x direction, so its total energy is given by the Hamiltonian H is equal to kinetic energy plus potential energy, so which is given by px square by twice m plus v of x. So let it be equation number 4. So I think equation number 4, so it is equation number 5. Let it be equation number 5. So now if you multiply this equation by psi on both sides, then you will get h psi is equal to px square by twice m psi plus v psi. That's what you will get. Now you see this px square by twice m, if you compare, if you go back to this equation, here you can see px square by twice m, this can be replaced by this part of this equation. Here you can see this is also psi, this is also psi, so that's why px square by twice m is it can be replaced by this. So hope you have understood. So now let us replace this here. Let us replace this by, so px square by twice m is equal to minus h cut square by twice m, second order derivative with respect to x. So let us replace this term by this. So then what you will get? You will get h psi is equal to minus h cut square by twice m del 2 by del x2 psi plus b psi. So here you can write this way: h psi minus h cut square by twice m second order derivative with respect to x plus b whole into psi. That's how you can write. Now here you see, as this Hamiltonian represents total energy, so that's why total energy operator is given by h cap, that is equal to minus h cut square by twice m second order derivative with respect to x plus b. So this is total energy operator, total energy operator, or you can say Hamiltonian operator. So that is Hamiltonian operator, and in 3D this will be replaced by this operator, Laplace operator. So let me write in 3D. In 3D, this is in 1D. In 3D, it will be h cut minus h cap minus h cut by twice m, h cut square by twice m, Laplace operator plus b. So that is in 3D. So hope you have understood this. So our next topic is Hermitian operator, and that topic will be covered in next video. Okay, so hope you have enjoyed this video, and if you have enjoyed this video, please hit the thumbs up button, and if you are new to my channel, please subscribe the channel, because that's inspire me to create new videos for you. So thank you for watching. See you in the next video.